I'd like to move ahead with the next presenter, Dr. Niels Harrit. Dr. Harrit is a chemist and former associate professor at the University of Copenhagen's Department of Chemistry. Niels Harrit has authored numerous scientific publications in fields such as nanoscience, photochemistry, and structural mechanics. Harrit gained international attention for his co-authored paper titled Active Thermitic Material Discovered in Dust from the 9/11 World Trade Center Catastrophe. If there ever was a more provocative title to a scientific publication, I would say this one takes the cake. Dr. Harrit, you have the floor.
Thank you indeed, and thank you for inviting me, and thank you for Redacted to provide their platform for this live transmission. My presentation is entitled The Chemistry of 9/11, a Coherent Collapse Scenario for the Twin Towers. And I will tell you about the NIST report on the Twin Towers. In the main summary, they provide on page 82, the most important footnote in my mind after the Second World War, according to which they admit actually that the timeline for the NIST report on the Twin Towers goes from the instant of aircraft impact to the initiation of collapse for each tower. The consequence is that there is no official technical account for the collapse of the Twin Towers. Did you get that? There is no technical official account for the collapse of the Twin Towers. And that is being revealed in this footnote. And so they admitted they know very well that this is the case. Now, instead, they claim falsely in the NIST report that they have demonstrated that up until that point, the towers is in such a poor condition that it's prone to collapse any minute. And then they leave and go home, which means that they leave it to gravity as the only force for doing the work. And the question is this is what we see here? Is this gravity? Not very much, as Richard Gage just demonstrated. What you're seeing here is building debris, girders, steel beams being thrown up and out across the street into the World Finance Center here, 100 meters. This is a beam about 15 tons. And here we are 200 meters from the North Tower, actually. And it's fragments the size of 4 tons being thrown up and out. Okay? I may remind you that gravity is vertical. Okay? It's game over. We're finished. Because it means the initial account cannot be true. And if a theory can only be wrong once. If you need some academic icing on the cake, you may refer to Sir Isaac Newton, who in 1687 wrote this famous book, and his second laws of motion say force equal mass times acceleration. The point here being that the force and acceleration are vectors, meaning they have a direction. In plain English, an object moves in the direction of the force. So for that, if you want that, you may refer to Sir Isaac Newton if you haven't recognized that gravity is vertical. So this is game over for the official story, as theory can only be wrong once. And we may stop here and take another break. But naturally, we start asking, well, what happened then? And for that purpose, I will introduce you to something called energetic materials. I'll give you an overview, a little chemistry course here. But first, we have to go through 4 fundamental concepts. We already met the force. And the force is something which can make things move, or it can exert a pressure. Energy is not a thing. Energy is a concept you use in calculations. It's a quality you assign to an object or a system. Heat is one kind of energy expression. That's one means that we realize that there is some energy coming out. And fourth, work is a concept we're going to need. It's the energy spent on the movement of a thing. In physics, work is a very, very mechanical thing. It all deals with moving things. So energetic materials, the best known kind of energetic material, of course, is gunpowder. It was invented by the Chinese in the 10th and the 9th century, and it consists of a mixture of pulverized charcoal, sulfur, and saltpeter, which is a chemical you can dig out from the ground. These are powders which you mix in a very macroscopic fashion, and I have to bother you with a little chemical equation here, but it's not so bad. Carbon, C is the symbol of carbon, S is the symbol of sulfur, KNO3 is saltpeter, and when it reacts, they are forming gases. Carbon dioxide, sulfur dioxide, and different nitrogen dioxides. And that's important. This is what an explosive does. It produces a gas very fast, so you get a pressure. And that pressure can do work. But in gunpowder, a chemical reaction is the movement of electrons. So in the gunpowder, the electrons have to move from the carbon onto the saltpeter particles. It takes a lot of time because the electrons are very small and they have a very long distance to move. Visualized below here, we have the carbon particles, and the electrons are having a very long way to go. So for that reason, gunpowder is very slow. It's actually not really an explosive. And you can use it in fireworks, you know that. And you don't want the rocket to explode. So in a rocket, the gunpowder burns from the top down very slowly, so the rocket goes up. For that reason, I would characterize gunpowder not as a real explosive, rather as a propellant or rocket fuel. Okay? So explosives, they make gas very, very fast. It's a misconception that explosives should be particularly energetic. They're not. The key here is they are fast. And the same thing with propellants. The propellants, they can develop a gas, they can do work, but they are not very fast. And lucky for that. So if you need an explosive, you have to cut down on the distance the electrons have to move. This is an example here. RDX is a very common explosive used for cutting steel beams and stuff like that. Cyclotrimethylene trinitramine here, and you have the formula here, and you can see here the electrons only have to move a very, very short distance from that nitrogen atom to that nitrogen atom, and that is a distance about 1/10 of a millionth of a millimeter. So that's why RDX is very, very fast, because electrons don't have to move that far. Well, RDX is the nasty explosive, because the combustion zones, it moves at more than 20 times the speed of sound. So the bang actually breaks the sound barrier. It really hurts the ears. I have told you about explosives. I've told you about propellants or rocket fuel, and we went back to take a look at the most common explosive called RDX, and it's extremely fast because the electrons do not have to move very far. So that is that the combustion zone moves at the speed more than 20 times the speed of sound, so the bang goes through the sound barrier. It's very noisy. Now, the third kind of energetic material I'm going to present today is incendiaries. And the best known kind of incendiary, which is something which can make a lot of heat, is thermite. And incendiaries, they can do heat, they cannot do work. Incendiaries cannot do work, they can only make a lot of heat. They are very slow, And the best known kind of incendiary is thermite. A little chemistry equation again. Thermite in the classical formulation, which goes back to 1893, is a mixture of aluminum and iron oxide powder. You may call it rust if you want. And then it reacts and forms aluminum oxide and molten iron. And it is molten because the temperature which is reached by this reaction can be extremely high, as much as 200 and 500 degrees centigrade, which is roughly 1,000 times above the melting point of iron. So, and now I'll show you what this combustion of iron here in the lab. And you should in particular recognize the little white cloud over here. That is aluminum oxide, and it is sputtering. Now I'm going to show you what thermite can do to a French car.
The engine block is the densest part of a car. It's basically a huge lump of metal, and, well, it's very hard to melt. Lucky then, the Brainiacs have plenty of thermite, specially packed into the slow-release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Within seconds, the fiery concoction eats through the bonnet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signalling the inevitable victory for thermite. A quick check confirms a clear path of destruction through the engine.
Now, if we think if thermite is supposed to cut the steel beams and the steel columns in World Trade Center, don't we have a problem here? Because on the French car, and let me add, I drive a French car. I've done so for 50 years. And because it's vertical, the action is vertical, how can you possibly cut a steel column which is in itself vertical? That problem has been solved, obviously. All you have to do is put the thermite into a container which can stand the heat, and then it goes like this. Here we go. That's it. You do it very fast. And actually, there are many patterns of this, what you call beam cutters. Let me tell you then about thermate, because if you want to cut steel, it will be advantageous to add sulfur to the mix. It has the effect of lowering the melting point of the steel, and as far as down as 992 degrees centigrade here. You may add other things. It's not very interesting in this context, but in the end, the mixture can cut through steel like a hot knife through butter. Adding sulfur to the thermite mixture, it leaves a trace. There's something to be found afterwards. And this is the publication which came already in December 2001, that is about 3 months after 9/11, where these workers from Worcester, they received some samples of steel beams from FEMA, and they investigated it in this analysis here. And what they found, well, here you see such a steel beam. It looks like Swiss cheese. It does not look like a steel beam at all. But if you go and take a closer look, this is metallurgy, you will find in it faces of iron sulfide. And this is how you do it. The technology is called energy dispersive spectroscopy. And you can see iron sulfide. If I can here, this is iron sulfide. No, this one is iron sulfide in here and up here. And that is a safe proof. The thermate, the variety of thermite, has been applied on this column. There's no way around it. So, and this is how you do it. I showed you before on the little steel beam, the cutter charts. There are many patterns, and some of them are military patterns. You may recognize the date is 2001 on this pattern, and this is how you cut a steel column by doing this. And that is the reason why we saw molten iron pouring out of the Twin Towers. This is molten iron. It is not molten steel. It's molten iron from the thermate acting on the steel columns. Thermite is slow, and it is slow for the same reason that gunpowder is slow, because the electrons has to move very far from the aluminum particles to the iron oxide particles. But it has a lot of energy. There's far more energy into the thermite reaction than into molecular explosives. So wouldn't it be wonderful if we could speed up the thermite reaction and we can add something which produces a gas? Then we'll end up with an explosive and rocket fuel. Enter nanotechnology, because what you do in nanotechnology is you make everything smaller, smaller and smaller and smaller, and you end up with dimensions which is about 1/1000th of a meter. That's 1/1,000,000th of a millimeter. Very, very small ingredients. And for that reasons, now, when it reacts now, the combustion temperature goes up and this time goes down, the speed goes up. So the coarse particles here go slowly, but as the particles get smaller, the temperature goes up and the time goes down. It reacts much faster. So, and there are many kinds of documentation that the military picked up on this technology. This is from a conference in San Diego in 2001. And I wish I could see the pictures down here on my screen in front of you, and I would read for you. I cannot read from this distance, actually, what you see here. Maybe somebody will help me. But I'll try the next picture, which is from MIT, Massachusetts Institute of Technology. And it says that the military reloads with nanotech, smaller, cheaper, and nastier. So now, to sum it up, the energetic materials in explosives, they're fast, they produce a gas. Propellants, they're less fast, not so fast, they produce a gas. Incendiary does not produce a gas. But when you move to nanotechnology, they are all fast. And if you add something to the thermite reaction, you will also get a pressure, and you can convert it into propellants and explosives. They can both be nanothermic. So in 2009, this picture came out, active thermitic material discovered in the World Trade Center dust, where we discovered something in the dust which looked like this. We call them the red-gray chips, and they're red on this side of it because iron oxide, most of it, some kinds of it, are red. It resembles rust, right? The most important findings, in my opinion, from this very big publication is the reactivity of the chips. I was actually surprised that they would still be reacting after so many years, because nano aluminum has a limited shelf life. But I'll show you now 3 videos which demonstrates that nanothermite can produce a gas. And the first one is from the lab of Stephen Earl Jones, where you see the experimentalist, he's holding a micro torch in his right hand, and to the left of the torch is a little nano red chip, one of the red-gray chips. They're about 1/10th of a millimeter. They're extremely small. But you see here in the video that the chip ignites and then it moves. It hits his hand and he could actually feel it. That's the moment, you see, it's moving. And when things are moving, there is a force, which means that a gas was evolved in this reaction here. Next thing is ignition under a microscope. I should credit Mark Basil, a chemist, for doing this. He put the chip on a hot plate and watched it under a microscope. And what you see here is the swelling of the chip, means a gas was evolved. And the next one is my friend and colleague, Kevin Ryan. He's making nanothermite in his backyard, not the original stuff, we cannot do that, but another recipe from Lawrence Livermore National Laboratories, and it goes like this. on a hot plate. And obviously the lid was blown off. It was not due to the heat. There was actually a gas being involved here, and that was carbon dioxide, for your information. Now we're going to take a look at the Twin Towers, and this is actually a very important video in my mind, and I credit David Chandler sitting in the audience. That was the video which made me snap my fingers to understand.
The starting point in science is observation. What you are seeing here is what happened to the North Tower of the World Trade Center, the second of 3 buildings to collapse on 9/11/2001. I use the word collapse, but words can be deceptive. What do you really see happening here? There's a tremendous amount of falling debris, but under the canopy of debris, do you see the rapid sequence of explosive ejections of material? Some of the jets have been clocked at over 100 miles per hour. I will call them explosions because it's hard to find other words that describe what we are seeing here. The explosions are not isolated and few. They are continuous and widespread. They move progressively down the faces of the building, keeping pace with the falling debris. Perhaps you can imagine a natural cause, but I can't. Notice that the explosions are occurring on multiple floors at once, over a wide zone, not in a floor-by-floor sequence that might be explained by pancaking collapse. Notice there are explosions far below the point of collapse. Some are isolated and focused. These are often referred to as squibs and are commonly seen in controlled demolitions. However, this is not a standard controlled demolition. The building is being progressively destroyed from the top down by waves of explosions, creating a huge debris field. The destruction is in waves, not just in one wave. Most obvious is a rapid sequence of explosions near the visible corner of the building. But simultaneously we can see another wave of explosions much further down the face of the building under the canopy of falling debris. Notice that both waves of explosions progress down the face of the building, nearly keeping pace with the falling debris just a few feet away. Slabs of concrete did not fall to the ground and smash to dust. There is almost no concrete in the rubble pile. Notice that the concrete is being forcefully ejected outward from the sides of the building, already pulverized to dust. Notice that embedded in the dust clouds are huge girders and entire sections of steel framing that are being hurled out of the building. The horizontal speed of some of the girders has been clocked at over 70 miles per hour. Some of these girders impale themselves in the sides of neighboring buildings. Some landed as much as 2 football fields away from the base of the tower. What could hurl heavy girders with such force and give them such speed? Some people have suggested that the weight of the tower crushing down on the girders caused them to flex, and they sprung sideways by a spring action. But we are not seeing isolated jumping girders. We are seeing a major fraction of the mass of the building, steel, concrete, office furniture, and the remains of human beings, reduced to small pieces of rubble and fine dust, and being explosively ejected in all directions. Bone fragments are found on the roofs of adjacent buildings. The bones were not crushed in the falling mass, or they would have been trapped in the debris pile. They were pulverized along with everything else and blown out in all directions. The NIST investigators have claimed that the top section of the building above the plane impact point came down like a pile driver, crushing the undamaged lower section of the building all the way to the ground. The top section of the building is, however, noticeably absent. There is nothing above the ring of explosions except for a fountain of debris. Can you see a pile driver? For this object to radically change directions like this, it had to experience a sudden impulse. We know there was a large amount of unreacted nanothermite in the World Trade Center dust. That was confirmed in a paper published in the Chemical Physics Journal in April 2009. Thermite reactions produce aluminum oxide, which is visible as white smoke, and nanothermite is explosive. Nanothermite is stable when wet and can be literally painted onto steel beams. Nanothermite painted onto this chunk of material would explain the explosion, producing the sudden change of direction, and it would also explain the white smoke trail. When we zoom in, we can see that the path zigzags, indicating multiple small explosions. Once I found this projectile, I looked for it in other videos. I found it in several videos from different angles, but when shown against the backdrop of the white debris cloud, it is very hard to see. This is another video from a very similar perspective to the first. In this shot, the trail can be seen to persist all the way down to the bottom of the collapse. We can learn several things from the behavior of this projectile. First, it is clear that this chunk carries explosive material with sufficient power to drastically change its momentum in a short outburst. Secondly, it is clear that the smoke we see is not general smoke from the fires entrained in the wake of a moving object. Since the smoke trail follows the object in all of its twists and turns, it is clear that the smoke is being emitted from the object itself. The most obvious interpretation, of course, is we are seeing the results of nanothermite burning and undergoing explosive outbursts. Once we see this clear example of an object trailing smoke generated on its surface, we can reinterpret what we are seeing elsewhere. There are lots of chunks of falling debris trailing smoke clouds. In many cases, we can see long beams with smoke being emitted from the entire length of the beam. We no longer need to assume that this is smoke following in their wake. When we see white smoke that looks as though it's coming from the girders, it is reasonable to assume that we are in fact seeing smoke coming from material painted onto the girders themselves. When we see chunks that race ahead of the rest of the falling debris, as we see near the bottom of this view, we can reasonably interpret this as caused by explosive impulses that increase the speed of these objects, just as they change the direction of the one we've been studying. It is time to take off the blinders. We have not only chemically detected nanothermite in the World Trade Center dust, we are literally seeing nanothermite in action. Once our eyes are opened, we can see it wherever we look.
Courtesy David Chandler. I may skip the next one because I'm a little short of time, and we don't need it really because David had take a closer look on many of the fragments, and you can see how they're exploding actually up in the air in the trajectory. Some people think that now if the Twin Towers were loaded with nanothermite, why didn't it take off after the impact of the airliners? First, you must remember there were no iPhones at that time. There were not many cameras around, but the few videos there are, you can actually see it did happen. There was actually nanothermite being ejected prior to collapse. Take a look at this one. Yes, please. What you see here are the particles coming out, okay? Bang, zig, 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 zig. It goes exactly like the one David Chandler showed you before. Zig, zig, zig. And it's before actually the South Tower had been hit. So, just for comparison, nanothermite is used as rocket fuel. Whenever you see a rocket taking off on your TV screen, as the one to the right here, this is aluminum oxide. Okay, we're finished. So if you want a coherent model, consistent model for the collapse of the World Trade Center Twin Towers, you would need at least 3 kinds of energetic materials. We have already heard that explosives were all over and they are noisy and you can hear them. Thermate was needed for cutting the columns. They are noiseless, they don't make very much noise, and they are thermitic by definition. Nanothermite for moving the bulk of the material outside of the bathtub. You may speculate why they did it this way, but nevertheless, maybe it was the canopy cover to cover what was going on. Maybe it was just shock and awe for everything. That's it, a coherent, consistent collapse model for the Twin Towers. Now time for acknowledgements. Friend of mine and co-worker on a nanothermite paper project. He has done many other things. Physicist David Chandler, he's in the audience, and he should be highly credited for his fantastic video work on World Trade Center. In my opinion, it has had greater impact than any scientific paper can do. And I envy his students. I wish I had a physics teacher like him 65 years ago. Professor Stephen Earl Jones is a master of the electron microscope on Brigham Young University, where he carried out most of the work which went into the nanothermite paper, together with this gentleman who initiated the nanothermite project. And now, in a little moment, I'm going to ask you a favor, because over the years, I have always wanted this gentleman to get the standing applause he so rightfully deserves. So for that reason, I wish to dedicate this presentation to a great scientist, a brilliant experimentalist, and a wonderful human being, Professor Stephen Earl Jones. Thank you. I can do a little, what do you call it, performance, illustrating what free forms acceleration actually means. And I'm sure that our friend David Chandler would know this. Okay, we have time. This is what I do to my students, because it tells something about the energy being involved in the process. Now, if you apply Newton's second law to how much will free fall take from 2 meters height, you come out with 0.66 seconds. So free fall from 2 meters will take a little more than half a second. But so I'll demonstrate this in a little while. I'll expose this underliner to free fall. But first I'll put it down on the floor. And it's lying down on the floor, and we all expect it to stay there. Not because it's not subject to any forces, because there's gravity pulling the underliner downwards. But the floor exerts exactly the same pressure the other way up. This is Newton's third law. And because the one force is equal to the other force, there's no resulting force acting on the underliner. So for that reason, it doesn't move. This is Newton. First, it's very easy. Now I'm going to do some work. As I told you before, work means moving of things. I'm going to do work. I'm going to move this thing 2 meters up in the air. And for doing this work, I have used energy, right? It comes from the breakfast I enjoyed a couple of hours ago. And the energy has been spent for moving the object 2 meters from the floor. And now it's up here. Now, if I release this object now, it will go into free fall. And that is where the energy I have spent to giving this object a potential energy, because now it is 2 meters away from where it wants to be, namely on the floor. Energy, nature always wants to go home. It wants to go home. But I have given this potential energy will be released in a second. And the energy I have given to the underliner now goes into accelerating this object down into the floor. We can make the experiment. Are you ready? 0.66 seconds. I count to 4. I release it on 3. 1, 2, 3, 4. And if we had done this experiment accurately, I promise you it would have taken 0.66 seconds to reach the floor. And what does that imply for us? It means that all the energy which went into raising the 47th floor of Building 7 up in the air in 1987, now on 9/11, went into accelerating the 47th floor down to the ground. That is, there is no zero energy left for doing other work, namely taking the whole steel structure apart. That is why the the free fall acceleration is important, as David Chandler has shown us so many times. Thank you.